Today lesson we learn transverse shear stress. Shear stress. In lesson 8, we learn the bending. We want to know how the bending moment create a normal stress and how that normal stress distributed throughout the cross section of a member. Today, we learn how the shear force, the internal shear force of a beam that create a shear stress and how that distributed throughout the cross section. And as you learn in the very first lesson, when we know tau, which is the shear stress, is equal to the shear V over the areas that the average shear stress distributed through the cross section is not the show how the shear stress vary across the section that we study. So that the purpose today. We want to know, okay, the internal shear force, how that create the shear stress and how that shear stress distributed throughout the cross section. So that's the topic we learn today. So with that, we work on the beam analysis. Beam analysis, and that you just learn about the shear and moment diagrams, and we already know how to draw the diagram for the shear, diagram for the moment, to identify where is the greatest shears throughout the beam or throughout the member, where the greatest moment throughout the member. So let's get the general any general loading. General loading for beam. If I have here beam and assume there are pins on one end and roller on the other end, and let's put any random distributed load on that member. So it don't need to be a uniform distributed load. It any random with distributed load is a function of x, and with x is from the left to the right with that member x here. You see the function of x. So with that, let's work on differential slice, something we done in shear and moment diagram with the distance dx with that differential slice and distance dx, and then we want to draw the free body diagram for those components here for that differential slice. So let's draw the free body diagram of section dx or the differential slice dx. So we have that component, and we have dx, and for the cross section of that member, just want to draw down what is the cross section look like for this member. If I cut that member, the beam, if I cut the member here, then the cross section, let's see, let's assume that cross section is a rectangle, and the thickness, we call that T, the thickness of that cross section is T, and that is equal to H for cross section of the member, like you do in the beam design. So with that, we cut the differential slice section dx, and as you recall, with that free body diagram, we have to show all the forces acting on it. So the first one, as you can see, it can be the distributed load in it, any random distributed load, and that is Wx. So it vary, don't need to be uniform. And on the left side of that differential slice, we have the shear force V, internal shear force, to have that to make that differential slide in equilibrium. And we assume a positive shear force, and also we assume positive moment. What is positive moment? Positive shears. Go back to shear and moment diagrams lesson when we learn designer side convention. And on the other side, the shear force is equal to V plus dV. So something here, nothing new if you already learn the shear and moment diagram, where we do the same with this, and M plus dm for the bending moment on the right side. And we also know something called neutral axis. So what is neutral axis? Neutral axis is the axis parallel to x or y axis, and in this case parallel to x and go through the centroid. So in this case, I assume that is a rectangle cross section. So the centroid, as you can see, it there, that is the centroid. So it goes through the centroid. So it's really in the middle. But if any kind of cross section, it don't need to be go through the middle. Just go to the centroid. And that is the neutral axis. We call that the NA. So nothing new for us.